Today's seminar, we're going to be confronting some ghosts, which is pretty exciting. We've got Dr. Cameron Naficy here from Oregon State. Dr. Naficy is an ecologist whose research focuses on landscape disturbance dynamics, social ecological linkages, forest mortality processes, and ecological thresholds in temperate forests of North America. He uses a combination of paleo-ecological tools, photogrammetry, remote sensing, and statistical modeling to examine these questions for historical and contemporary environments. Dr. Naficy is the founder of Greenfire Geomatics and is a research scientist in the Department of Forest Ecology and Society and the Landscape Ecology Modeling, Mapping, and Analysis group in the College of Forestry at Oregon State University. He completed his PhD in geography at the University of Colorado in Boulder, a Master of Science in the Division of Biological Sciences at the University of Montana, Missoula, and a BS in Ecology and Evolutionary Biology at Rice University in Houston, Texas. He's a former Fulbright Fellow in Argentina, where he studied the ecophysiological mechanisms of tree death in Patagonia forest. And I know that he's currently working with some of my colleagues or previous colleagues with the Karuk tribe in the Klamath River, which I think he might touch on a little bit today, hopefully. His talk is titled Confronting the Ghost of the Fading Record in Paleoecology, using multi-proxy historic records to reveal historical fire severity dynamics. So thank you for joining us, Dr. Naficy.
Thanks, Jill. Thanks everybody for coming. I'm excited to be here, fly way far down south for at least an hour or so here. I'm going to be talking today, kind of take an overview approach to a number of projects that we've been working on to bring to you some of the highlights of what we've been working on. I'll start out with kind of some methodological questions and ideas that we've been grappling a lot with over the last few years. And then really what I want to try and do is dig into sort of the highlight reel from a couple of different projects now where we've been working and applying these methods with a real emphasis on dendroecological reconstruction of fire severity. So that's the overall outline of what I'll be talking about today. I'll start with this idea of the fading record in paleoecology, which has been talked about a fair amount in the literature. Here's a definition from Tom Swetnam. And really, this is a problem that we contend with in a variety of paleoecological scenarios and data types as a result of missing data. It is sort of hand in cart with what we do in paleoecology. It's always there. It's always something that we have to deal with, but it does take different forms in different types of paleoecological records and with respect to different research questions that we might be pursuing. And so the degree of problem that it presents is also variable. And this is something that I think has received maybe a little bit less attention in paleoecological literature. It's sometimes talked about as kind of a monolithic fading record problem, when really it's a variety of fading record problems that also have a variety of solutions. And that's what I wanted to lay out in this next slide here. Of course, when we talk about missing data, R.A. Fisher here said the best solution to handle missing data is to have none. And that usually just isn't an option for us in paleoecology. And so we have to step into this world nonetheless. But there's a useful statistical framework that exists within mathematics and statistics to deal with missing data. And they've built a system, a classification system for missing data problems that are referred to as MCAR, MAR, and MNAR. So missing completely at random, missing at random, and missing not at random. And here's just sort of a graphical representation of what these look like in data space. And really the key to be aware of here is whether the variable of interest, sort of your Y variable, is related to the response propensity in the data. And that's what's shown in these graphics here. In the case of missing completely at random, there's no association between the missing data, which is shown here in red, versus the full data in black. and your Y variable. In the case of missing at random, there is some missing data, but it's biased within X and not within Y. So it doesn't necessarily bias the response of interest. And then in the case of missing not at random, we actually have biased data with respect to our variable of interest. And this is, of course, the most problematic of the cases. So these first two can be considered ignorable, or they're relatively simple ways of dealing with some of these. The last case is a case that is really not ignorable. And this is explicitly the case that we're dealing with when we talk about historical reconstruction of fire severity. Generally, the methods that I'm going to talk about now depend on association between fire dates within fire scar records and age structure data. And the amount of missing data that we have in age structure data is specifically related to severity. And I'll show you what that looks like a little bit here. And this differs from some other paleoecological cases. So if we map this out, thinking about some of the different dendroecological applications that are common, here's a tree ring growth example where you could see that we have these different, you can see my arrow here, where you can see these three different chronologies here that overlap in different amounts. Here's the sample size curve up on top. And we could, in red here is highlighted the percent of the record, or the proportion of the record that is influenced by, say, low sample sizes, right, which is a form of missing data. And you can see that here then sort of in data space. And so one of the solutions that people have used for this is just when we get very low sample sizes, we tend to truncate the records. I think the record is no longer robust over certain periods. And people have taken a similar approach in fire history reconstructions, where we use fire scars from individual or plot composites to reconstruct fire history over time and fire dates over time. And again, oftentimes when we get below a minimum sample size, records are truncated. And that's how we deal with the parts of the records that we're least certain about that have the most impact from the missing data problem. In the case of fire severity here, what I'm showing you here are sort of representation of age structure plots and what the data actually looks like, where we associate both fire dates here shown in red and establishment data, or survival data is another way to look at this, from tree cores. And in this case, what you can see is that the degree of influence of the missing record problem and the missing data problem is really throughout after this first fire in particular. So it pervades the very metrics that we're interested in, the very behaviors that we're interested in, and makes this really a wicked problem where something like truncation is not feasible or so severely limits the record that it's undesirable. And so this is the basic conundrum that we've been sort of grappling with over the last several years. So I'll present to you now one of the ways that we've been trying to get beyond this and dive into this question nonetheless. This is a graphic based on an association of tree density. This is the density of survivors versus the number of fires. And this is based on work that Alan Tepley did, in particular a paper from 2015, where he created this association. And what I'm showing you here is a number of the behaviors and the metrics that we've been using based on this graphic to understand and measure fire severity. So what we're looking at here is for each site, how tree density declines as a function of the number of fires. And you can do this for individual sites, or you can bin this and you can look at average behaviors. And there's a few key metrics that I want to bring to your attention. One is what we're calling the event level severity metric that focuses on how much the tree density declines for each individual event. And so this is proportional to severity for individual points in the landscape, wherever you're sampling, and for whatever fire date you're interested in looking at. And then there's another one here, lambda, which is a time integrated fire severity metric, which is essentially the average slope that we see at a given site. So across all fires at that site, what was the average rate of decline, which again is proportional to severity, but in this case, it's time integrated severity across all different events recorded at that site. And then this final metric is what we're calling the stand replacing equivalent, which we can measure in units of time or number of fire events. And essentially what it reflects is when you get total turnover of trees at a site. So it's sort of like a cumulative high severity. How many fires or how much time does it take before you completely turn over the trees at that site? Part of what we've been doing with this work recently is trying to scale up our efforts and look at cross-study analyses. I've compiled a data set with most of the sites I have data from that are displayed here, not all yet, some are in the works or hopefully in the works. But this shows the biogeography of where we have samples, what kind of forest types they cover, and what kinds of time frames they cover. And there's a couple purposes to this data synthesis effort. One is the event level severity metric is a relative metric. And so it really tells us how much something moved as a result of any given fire event relative to others. This is one of the ways that we got around, in a sense, the fading record problem, but it means that it's not an absolute fire severity metric. It's a relative metric. And so part of the purpose of this larger study is to help us begin to calibrate our severity estimates and dig into the question of how this is representing what we conceive of as real fire severity. And of course, the other purpose is some larger scale ecological analyses, understanding biogeographical patterns and other sorts of behaviors in the data. So real quick, what I'm comparing here is this event level severity metric, delta S, where when we calculate it based on individual studies, which is what we've done for the most part previously, versus when we pool it across this larger data set. And what you can see is that there's some correspondence, but there's a definite bias in the data. And that bias is related to the inputs in each study. So that both the magnitude and the direction of this bias is related to essentially how diverse the data set is in terms of the fire regimes that it represents. If it's predominantly high severity or predominantly low severity, you'll experience more of a bias than if you have a good mix in this data set, because again, this is a relativized metric. And when we use the pooled data set from this broader synthesis effort, and we compare the relative metric, which is delta SN, to lambda, which is a time integrated metric that is absolute though and not relativized, what we see is relatively good correspondence, whether we're looking plot to plot, whether we're pooling data by individual studies, or cover types. And so this suggests that the calibration that occurs when we use this much larger data set is really improving the relative nature of this event level severity metric and moving it more towards an absolute metric, which is really what we want. So one of the things that we're interested in doing with this, for a long time, there's been work that has these sorts of cartoons of historical fire regimes or even modern fire regimes, where we look at the frequency and the severity of fires to define where certain sites or areas fall within that space. But there's been some real challenges in sort of producing these simple graphics that come from the fact that oftentimes these efforts rely on sort of expert opinion, individual studies, qualitative comparisons across studies. Really, the driving factor behind all of this is that we haven't had a standardized quantitative cross-study metric for quantifying fire severity in dendritic ecological records. And so one of the neat things that we can do with this is begin to make some of these attempts with a data-driven quantitative approach, where we use things like the median fire interval and the mean severity to plot forest types in that space. I'll show you these kinds of graphics a number of times. Here we're looking at lower fire severity with lower values and higher fire severity with higher values. And these dashed vertical lines represent, I think it's the 30th and 80th percentile cutoff. So these are sort of akin to where we might draw lines for low and high severity thresholds within this gradient of fire severity. Down on the bottom here, I'm showing the stand replacing equivalent, which is another way of looking at severity related dynamics in these ecosystems. And we see some patterns that make sense to us, right? We can see things like ponderosa pine in pink here being down towards more frequent lower severity fire regimes, moist mixed conifer forests, for instance, falling at intermediate levels, so on and so forth. I mainly show this to demonstrate the types of analyses that we are sort of that we're tapping on the door of, rather than specific patterns, but I'm going to get into some of those in a little bit as well. Here's one example. This is an ecosystem that I've worked a lot in, these pure Douglas fir forests that characterize the areas you see here in brown. These are systems where ponderosa pine is absent, but we also find multiple fire scars on trees within these ecosystems. And in the absence of data, which we haven't had much of for these ecosystems because of the association between frequent fire and a lot of assumed properties of fire regimes, things like the ponderosa pine model have sort of been applied to these ecosystems at times. If we look at in our synthesis data set and we plot some of these different forest types out, ponderosa pine forests fall down here, and these Douglas fir forests, you can see have some overlap in terms of potentially both severity and especially fire frequency, but really you can begin to see how these things fall out and what some of the critical differences are between these ecosystems. And this is really just a benefit of being able to quantitatively assess and evaluate these properties rather than basing this on qualitative interpretations. This is another example just showing for one study area in Montana for two different sub-watersheds, one in the Swan Valley here in a broader, flatter valley, and one in a more constrained topographical environment, more within the montane zone. Both similar forest types, Douglas fir, large ponderosa pine, but here just looking at the ponderosa pine stands that were measured in each, both of them had very similar fire frequencies, but you can see how they really spread out or discriminate along this fire severity gradient. You can see their aggregate patterns of fire severity here, red being high severity, yellow being moderate, and green being lower severity. And so again, these are systems with very similar median fire intervals, but very different properties, both in terms of the severity patterns they were experiencing, some of the temporal dynamics of that, and the regeneration patterns that emerged from these as well. And it's really only by explicitly examining the age structure data and the fire severity patterns that we begin to reveal some of these differences. And actually, interestingly, in both cases, neither one of these forests fit sort of the classic all-aged representation of low severity fire regime models in ponderosa pine, like you might see from one of the sites in our data sets in Utah here. In this row are the spotted bear sites, which you can see are mostly young. They're oftentimes multi-cohort, but they were younger sites that had experienced a mix of both high severity and non-stand replacing fires. But even the Swan Valley sites, which were much older forests in general, had some interesting patterns where there were clear high severity fires way back in the record, and then a total lack of ponderosa pine regeneration for, in some cases, multiple centuries. So we're still sort of looking into this and trying to figure it out. But these are some of the clues that we're only able to examine when we look explicitly both at the age structure, the severity data, the fire frequency data. So I just want to go through kind of a highlight reel of some of what I think are the most interesting findings that we've had from a few of these different systems using 4 case studies. One is resilience to high severity fire in mixed severity fire regimes, specifically some of the ecological implications of this fire severity switching, which we observe, and I'll explain. Unexpected resilience in a fire sensitive forest, and then hopefully, if we have time, some interesting results related to indigenous fire practices within a couple of different ecosystems. These are the study areas that I'm going to draw from that we've been working in over the last several years: the Southern Alberta foothills in the Southern Canadian Rockies. This is east of the Continental Divide, west of the Continental Divide in the same ecosystem essentially, but on the west side of the Continental Divide in Montana is the Northern Continental Divide ecosystem, and then the Greater Yellowstone ecosystem, where I've done some work in the northern portion of this range. The NCDE, as I'll call it, is an environment that spans dry to moist mixed conifer forests. So ponderosa pine down low, and then Douglas fir, large lodgepole pine up into the subalpine, a fairly diverse ecosystem. The Greater Yellowstone ecosystem, we were working really within the dry, lower elevation forests. These are almost predominantly pure Douglas fir. This is above the growing limits of ponderosa pine, which is why it's absent. So you'll see some juniper or limber pine mixed in, but they're basically predominantly pure lodgepole pine, as you see in this picture here, and really haven't been studied very much. And the Southern Alberta foothills here, there are kind of two predominant zones here. This area borders the Great Plains here and sort of grades from pure Douglas fir forest, similar to the Yellowstone area, into and the broadest regions occupied by these lodgepole pine and aspen forests. So these are the study areas I'm going to be talking about. I'll present a series of graphics related to the sort of general findings in terms of some of these fire regime properties that we found for each of these, the NCDE, GYE, and Alberta here, with a gradient of forest types that are found in each, represented from the driest to the more moist type. So DMC is dry mixed conifer ponderosa pine, dry mixed conifer without ponderosa pine, dry Douglas fir, pure Douglas fir, moist mixed conifer forest, mixed wood, lodgepole pine, and spruce forests. I'm going to try and stay at kind of a high level here rather than dive into some of these details, because what I want to do is just show you what these mixed severity fire regimes look like and what some of the general similarities and differences were between them. In terms of fire frequency, which you're looking at here, you can see that most of these ecosystems had intermediate fire intervals. They were lower in the case of drier forest types and got a little bit longer in NCDE. They were intermediate between around 40 to 60 years for the GYE, and actually surprisingly frequent here in Alberta. And I'm going to talk about this in quite a bit of detail later on. In terms of some of the fire severity patterns that we can arrive at from this delta S, the event level metric, what we see again is a sort of an increasing gradient of severity as we go from dry to moist forest in NCDE. The GYE was a really mixed ecosystem, a lot of high severity fire, but a lot of non-standard places fire mixed in. And in Alberta, in the two main forest types that we have, the pure Douglas fir forests were really quite a mix, again, similar to the GYE. And the lodgepole pine forest had a really, the majority of events were high severity fire, but there was this important component of low and moderate events that I'm going to talk about as well. And if we kind of use this to look at the time integrated influence of severity for individual sample locations in the landscape, what we see is that a lot of them were actually quite mixed, so that there's different proportions of low and high severity fire, but in most cases, this is mixed in with high severity fire for most of these forest types. That's the orange color here. So these orange sites were areas that had recorded high severity fire, but also recorded low or moderate severity fire, whereas the red are areas that only recorded high severity fire. And the green, for instance, were the ones that only recorded non-lethal effects, non-stand replacing effects. And then in terms of stand age, the NCDE had really interesting variation in stand ages. Some older forests, some very old forests, and then quite a lot of younger forests. All of these are stand ages at the time, at around 1940, which is around the time when fire exclusion became effective in these ecosystems. The GYE had more intermediate and some older forests as well, as did the Douglas fir component of Alberta. And the lodgepole pine, which was the most prominent, had really young forests and actually pretty consistently in constrained range of forest ages. So I want to talk about resilience mechanisms in these mixed severity fire regime forests, especially in the context of this idea of sort of high severity fire begets high severity fire. This is an idea that's in the literature, especially with contemporary fire severity patterns. And it's the idea that, you know, a lot of these systems used to have feedbacks that kept them within this lower severity fire regime model. And if we get major high severity fires now, they can sort of get pushed over into this high severity fire regime feedback. You lose the fire resistant trees, you get more fire sensitive, either species or age structures. There's shrub and grass competition. And so you can get stuck in this feedback once you have a high severity fire that may represent a tipping point in some of these ecosystems. This is sort of been borne out in some of the remote sensing examinations of fire, where we see things like positive associations between the severity that occurs in the first fire versus the severity that occurs in subsequent fires. So you can see here in a paper from Brian Harvey, they found that for a variety of different forest types. And there's been a number of studies that have showed some of these same sorts of patterns. And so this seems to kind of confirm some of these ideas that if you get high severity fire, you may get stuck sort of in that high severity fire feedback. So to look at this with our data, one of the things that we did was we calculated what we call a lethal, non-lethal interval. And that's what's displayed here in the box plots for these same forest types. And what it is the interval in between a high severity fire, if a site experienced one, and a non-standard placement fire, either lower moderate severity, if it followed that, right? So high severity fire followed by non-standard placement fire, what's the interval in between that? And we calculated that for each site and grouped them by forest types. And there's some interesting things that we see. One is that really a high percentage of our sites seem to escape this high severity fire feedback, right? So they experience high severity fire. We have documentation of this in our records, but the next fire was not a high severity fire. It was a non-standard placement fire. And so it's this idea of switching between high severity fire and then coming out of it. And the intervals here over which that occurred depend on the forest type a little bit, but they tend to range between about 30 to 60 or maybe 80 years in some cases. And what we think essentially was happening, our data can't actually speak to this, so this is our interpretation, but we're interested in doing some follow-up studies to really dig into this, is that these after high severity fire, we're all familiar with some of these flammability curves and the idea, especially in Western North American systems, that as with time since fire, things like fire risk or fire hazard increase, right? So as fuels accumulate, there's a higher risk of high severity fire because of these flammability curves, which can have slightly different shapes, but the relationship tends to be positive. And what I think was happening in a lot of these cases was that these fires following high severity fires that were non-standard replacing were happening at times when there was still relatively low flammability within these ecosystems. So they hadn't sort of gotten over that cusp of being really flammable. And this may be the mechanism that explains why we were able to have some of the switching. This is an image from Montana in the Lola National Forest, an area that burned in 1987. So it's 29 years post-fire when I took this photo. So it's beginning to get into that range of where we think fires were starting, non-standard replacement fires were beginning to get into these ecosystems and reburn. And you can see, if you look at the heterogeneity of fuels and of regeneration, and imagine what a fire would do in something like this, you begin to see the heterogeneity and the interesting role that it might play, the spatial heterogeneity, and the role that it may play in allowing non-standard replacement fires to occur in these types of conditions. There's been a number of studies like this one from Dunn and Bailey where they've looked at fuel profiles and their evolutions across with time since fire. Some of them get almost to the range where our data suggested that these reburns occurred at lower severity, but oftentimes not quite there. And the other thing is that it's also very hard to integrate each of these individual components into, well, what actually happened in these fires? What are the probabilities here in terms of real outcomes? If you look at these environments, you see that they're filled with fire-sensitive tree life stages, very low crown base heights, thin bark. There's lots of fine fuels. There's lots of exposure, which means fuels could dry out and wind potentially could carry. But a lot of our fire behavior modeling has been done in mature forests. And so there's some real questions of how that applies within these younger environments and how much work needs to be done to really start looking into this with things like fire behavior models to understand how different they are, how the models perform in these environments, and then what they say about the ecology of fires. And then here's just one aerial image of an area in the Bob Marshall Wilderness in Lodgepole Pine Douglas Fir Forest that burned. This is a reburn. So showing some of these same behaviors actually emerging in modern wildfires. This is an area that burned in 1988, pretty high severity. You can see the distinction in the forest heights here where it burned. And then in 2013, 25 years later, it reburned. And you can see the patterning. In some cases, some of these areas got pretty blown out. In other areas, not, right? And so this is, I think, what is akin to what we were seeing in our historical data that's in some cases playing out in modern data or modern fires as well. So I want to talk briefly about some interesting ecological implications of this switching, this fire severity switching in ecosystems. This is some data from Camille Stevens-Ruhlman and Penny Morgan, where they went in and looked at areas that had burned in different sequences. And so that's what these refer to here, whether it was high severity followed by high severity, high versus low, low versus high, so on and so forth. And they look at a couple of different characteristics. Here is seedling density. This is the case that we see quite frequently in our data, in our historical data, a high severity fire followed by low. And what they show here is that those stands had intermediate stand densities, right? So you probably get this burst of regeneration if you get regeneration. It can often, this is from the Northern Rockies also, just as context. So you can get fairly high post-fire seedling densities, but when this second fire comes through of lower or non-stand replacement severity, you end up with these intermediate tree densities. And this is really quite consistent with a lot of what we saw in our historical reconstructions as well, where a lot of these areas that had a high severity fire, shown here in red, followed by one or more non-stand replacement events, tended to be lower density sites for this region. These are not high density sites compared to a lot of our other ones. And then there's some interesting ecophysiological implications of this idea of low density younger stands. This is some work from Bennett et al., where they showed that both growth rate and mortality rate were influenced by tree diameter. This is from a sort of a meta-analysis that they did. And so in both cases, smaller trees had higher growth rates, even in the face of drought disturbance, and lower mortality rates. This is a study by Mike Shadell, where they looked at areas in Montana as well, in the same ecosystems that we've been working in, areas that were clear cut and then thinned subsequently. So this would be akin to a high-low disturbance event versus those that were only clear cut, so only a high severity event. The thinning occurred about 10 years after the initial clear cutting. And here you can see an example of one that was a historical image of one that was clear cut and not thinned. So this is the high scenario, and one that was clear cut and then the regeneration was thinned. And here they are in sort of modern times. And Mike Shadell went through and looked at a number of different properties of these different treatments and influences on things like stand structure, growth. Here's a depiction of the different height changes for some of the different scenarios. And here are some graphical representations of a couple of different features: height to diameter ratios, merchantable volume, mortality rate as a function of stand age. And here the unthinned, so this is just the high severity scenario, is in gray. It's the gray line in each of these. And the colored are different post-thinning densities. So they use different gradients. But what really sticks out is the difference between the unthinned case, where you have shorter trees, less volume, and higher mortality rates, compared to these scenarios where you had a high severity event, clear cut in this case, followed by thinning relatively early on in stand development, which is the case of what our data was showing about historical fire regimes. So an interesting insight into what might be some of the really strong and multi-decadal long-term impacts of this severity switching and non-stand replacing fire effects early on in stand development. So we've done some positing about sort of different models of fire influences on ecosystems. There's some pretty nice ones out there. Fire is a global herbivore. Sort of fire is a spring cleaner, which is the classic sort of fire severity model from things like, or low severity fire model, I should say, from places like ponderosa pine forests, where you have these low severity feedbacks. In this case, what it seems like we think we're seeing in a lot of the ecosystem we've been studying is sort of fire as a predator, fire that culls out a lot of old forests and does leave some. So we're not making a case that there's no old forest in these areas, but it tends to be quite patchy or consists of these sort of low density, sparse remnant trees that are scattered throughout the landscape. And instead, fire maintained sort of young to intermediate age forests within the landscape, but these forests were, despite being young, were oftentimes complex, both in terms of within stands having multiple age cohorts or expressing quite a lot of beta diversity, so differences between adjacent stands. So this is kind of a different conception of how fire influences an ecosystem. And here we've put, one MSFR model, recognizing really the mixed severity fire regime concept is a gradient-based concept. And it probably is the case that there is not just one single model, right? Really what we're talking about is gradients and where things fall within the gradient of dynamics. The third case study is an interesting one from Alberta. I'm going to focus within this Alberta ecosystem, and I'll start by talking about some of the work in Yellowstone that Monica Turner and others have done. Really, this ecosystem is one that continues up along the eastern front of the Rockies here, and so it's a very similar or almost the same ecosystem. At least there's quite a lot of parallels. And if you look at a lot of their work here, what they have done is make a really convincing or evocative case that climate forcing of fire regimes in these areas is likely to lead to potential ecosystem collapse, or at least some real tipping points within this ecosystem. And they brought up these questions of will the ecosystem sort of be able to adapt to these, or will it reach tipping points and largely convert to, or in part convert to non-forested ecosystems. And they have done some interesting climate projections and built maps like this one here, where it shows that you begin to get below 60 or even lower 30-year fire return intervals. And this is where they seem to think that sort of ecosystem collapse is a possibility. And they're also very straightforward about the fact that these are fire climate models. They don't include a lot of the feedbacks that we know really ultimately are important for driving what kinds of responses we're going to see in these ecosystems. So the reason I open with that is because the lodgepole pine forest, which was really the major forest type we were looking at in Alberta, presented us with a really interesting empirical opportunity to look into this question. We documented really high fire frequencies, especially for this forest type. So you can see here, if you look at the lodgepole pine forest type, our median fire frequencies in the montane zone were about 25 to 45 years. Very abundant fire scar evidence in portions of the landscape. Oftentimes, initial scars were when lodgepole pine trees were really quite young, very fire-sensitive age, and a fire-sensitive species. So we have a lodgepole pine system with very frequent fire, where we can actually begin to look at and maybe test, or at least address some of these hypotheses put forward about vulnerability and tipping points. Here's our different forest types within Alberta laid within the fire regime space. Here, if you look at lodgepole pine, well, let's look at Douglas fir here first. So you can see that compared to where we found the fire regime space for other Douglas fir forests, within Alberta, it was quite a bit more frequent fire and lower severity. And really the same is true, excuse me, of lodgepole pine forests as well. You think about traditional models of lodgepole pine forests, these are long interval fire intervals on the order of 80 to hundreds of years in some cases, and usually thought to be quite severe. What we found in this ecosystem is that they were really quite frequent and relatively low variability, and a range of fire severities, including non-stand replacing fire effects. But we did find that the median SRE, stand replacing equivalent in terms of the number of events, was, I think this is the median here, is about 2. So on average, trees within the lodgepole pine trees were only surviving 2 fires. So there was a lot of mixed effects going on, a lot of complex dynamics going on, but it was a very transient landscape that was turning over relatively frequently. And the result of that can be seen here at the onset of fire exclusion. As I mentioned before, stand ages, especially in the lodgepole pine zone, were really quite low. There were stands that were only a few years old, but the median even was quite low, around 20 to 30 years. A proportion of these stands were complex, though, if you look at within patch age structure. So they had multiple cohorts. That's what the green and blue are showing here. But almost an even more interesting outcome here is looking at the percent of patches recording. If you look in these insets here, the percent of patches recording each individual cohort. And what you see for lodgepole pine in particular is that most cohorts most patches were not recording cohorts that were recorded in adjacent patches. And so what this suggests is quite high beta diversity. So patches that may have been high severity adjacent to each other, but not from the same fires, kind of an interweaving of fire boundaries mixed with some of these interweaving fire effects. And this is what produced complexity in these lodgepole pine forests, in this ecosystem under very frequent fire. And so we've done a lot of work with some of our management partners there to try and get people to sort of reimagine the foothills forest as young, complex, and in flux. And you can see that when you look back at some of the historical imagery, just how much the landscape has changed. I'll do that just real quick one more time. And if you look at these historical images, these are from the 1890s to about the 1940s, what you see is, again, a very young landscape. These are aspen trees that are not much taller than a person. Some of them have been burned twice. These are young aspen trees that were burned, again, next to a stand that didn't reburn. Lodgepole pine trees forming these kind of open, sparse areas, in some cases amidst aspen or more pure lodgepole pine forest. But all of this is really young forest, and it goes on across huge portions of the landscape. This 20 to 40-year-old post-fire landscape. You can see some of the fire patterning pretty interestingly in some of these cases that produce the age structure that we then came back and measured. So really interesting to look back at these images, I think. And you know what we sort of boiled this down to, this was kind of a wonky way of presenting our project name, which was Landscapes in Motion, but that this was very much a landscape in motion. And really to drive this home is what this meant in terms of the lived experience that each of us would have had within this landscape, is that within each of our lifetime, this landscape would have changed not only once, but probably multiple times. And this is a very different way of living in a landscape than I think most of us are used to. And it may have been much more common before. And it speaks to some interesting ecological resilience of what is a fire-sensitive forest to very high fire frequencies. And so this sort of has emerged to us as kind of an ecological surprise coming from this work that I think deserves a lot more digging into, obviously. And then the last thing I want to talk about today has to do with Indigenous influences within the same landscape. I'll be focusing on the landscape that we were working on here in Alberta. This is our study area here. This is a landscape that was lived in by the Niitsitapi with the four primary bands, the Amskapi Pikani, the Gainai, the Pikani, and the Siksika, as well as a few other tribes, the Sutina and the Nakota. And this is an area that has still to this day just a huge obvious influence of these cultures that were living there, that are still living there. The black here shows their existing systems of reservations. And here I've just highlighted a number of the major archaeological sites and known places of cultural importance, just to give you some examples. We started thinking about this a lot because we had documented these very frequent fires, especially in the lodgepole pine zone. And if you look at lightning data, which we have only since about the 60s, you can see here, this line represents the continental divide. So our study area is on the east side, and there's this real lightning shadow on the east side of the Rockies. And yet we had, of course, this fire evidence. And in many cases, and about 40% of fire scars actually were within this intra-ring position that suggested early to winter spring fires. And so this is a strong suggestion that this may be due to cultural fire use, because winter and spring are not times when we have abundant lightning, not times when fires are likely to start without human initiation. And then there's some confirmation of this in observational records. Peter Fiedler in the late 1700s wrote this: every fall and spring, and even in the winter when there is no snow, these large plains, either in one place or another, is constantly on fire. And when the grass happens to be long and the wind high, the sight is grand and awful, and it drives along with amazing swiftness. Evocative stuff, but interesting to have an account of this. We have been doing some looking at seasonality in our fire records in relation to fire severity. So what I'm going to show you here is for the Douglas fir forests in this column, and then for lodgepole pine forests in this column, the fire severity metric. So higher fire severity is up here, lower fire severity is here, in relation to the timing of, or the seasonality of burns based on the fire scar location. This is actually a fairly complex problem we had to deal with to interpret seasonality. We can talk about that later if there's interest. But what we find in the Douglas fir zone is not a very strong relationship between the season of burn, the inferred season of burn, and fire severity. And in the case of lodgepole pine forest, we find really interesting, I think, and contrary to expectation, a result that spring fires were actually of higher severity. So this suggested that the fires that were being used by the local cultures in the springtime or wintertime were of higher severity than they were than wildfires were sort of in the summer. I'm going to continue to dive into this a little bit, but I want to make one thing clear, which is that more severe fire is not the same as higher intensity fire. So I'm not trying to convey the idea that they were sort of setting raging conflagrations, and not saying that high severity fire also means large scale high severity fire, right? This may be controlled, constrained use of fire, which actually we'll talk about next. And then also I want to really point out that we are talking about this in the context of a forest that is fire sensitive. And in these fire sensitive forests, you can get decoupling of the type of fire, things like fire behavior and the outcomes or the effects of that ecosystem. And that's what I think that we're seeing in a lot of these cases. So this is our study area here. These colored polygons represent where we collected fire scar samples. There's a close up here. And these are some of the fire dates that come out of that aggregate record. Here on the y-axis, the percent of patches recording. And what we did is just color coded these by the percent of patches that we're recording to give us a sense of how widespread or how large some of these different fire years were. So red are very large fire years, yellow are intermediate, and these green and blue are sort of more local fire years. And I'm only going to talk about the record from 1700s on because that's really when it's more robust. The main thing I want you to see when we overlay sort of the cultural narrative that was going on at this point is that around the late 1800s, the 1870s, the 1880s is a major cultural transition. This is when reservations were being formed, treaties were being signed, the Blackfeet and other indigenous cultures were being transferred to the reservation system. The buffalo were exterminated in the late 1870s or 1880s. Railroads were being constructed in the area. And this has been called sort of the end of the American frontier, both in this time and in this place. And what we see in the fire record immediately following this major cultural transition period is not that fires end. In fact, large and sort of intermediate sized fires continue in the record, some very well-known years like 1919, 1910. But it's the small fires that disappear from the record. It's these blue and green fires that largely wink out around the time when this cultural transition goes on. And eventually then sort of fire exclusion shows up in the 1930s when sort of all fires are put out. And this is around the time when much more mechanized equipment is available. I think for time's sake, I may skip over this or I'll just go over it real quick. But one of the things that we see is that we built some models to look at the influence of median fire interval on a variety of fire regime and age structure characteristics. And what we see is this tipping point at around sort of 50 to 40 years for each of these different characteristics. So as your median fire intervals decrease, sort of fire frequency increases, we're getting these transitions into different fire regime dynamics, which may be part of what explains why we don't get these large scale transitions that have been predicted. And the last slide that I'll talk about here is just how this has made us do a lot of thinking about the contrasting models of human influence for different types of landscapes and landscapes with different types of forests. A lot of the way we think about these has come from dry and dry mixed conifer forests like ponderosa pine forests, where human influences sort of layer on to what we would call the natural disturbance regimes. Frequent fire gets a little more frequent, low severity fire gets a little lower severity, so on and so forth. But it doesn't take these in a largely divergent path. And what we think is in this this fire sensitive forest, it's really changed the way this landscape may have looked in a variety of these different variables. And I'll end here with some just very broad level conclusions. One is I think there's some really exciting and important paths forward for looking at historical fire severity. I think there's some really strong benefits of multi-proxy approaches to looking at this question. There's some interesting and unique ecological dynamics and surprises that I think emerge when we dig into some of these mixed severity fire regimes. And there's some interesting potential for looking at this question of social ecological systems that many of us have. And I'll end there.
Okay, thank you. I give you a virtual round of applause. I love a mixed severity fire regime, so cool. So for now, we can take some questions before the discussion seminar.
Oh man, I struck out.
It was a really cool talk. I appreciate all the insights, especially how unique mixed fire severity regimes are. Do you think that they're all kind of like this?
No, I think, I mean, this is what's really been satisfying and intriguing about some of the methods and the ability to look at these on a quantitative scale. I think, you know, there've been criticisms of the concept of the mixed severity fire regime, because you could argue that, well, everything's mixed on some temporal or spatial scale. Is it a useful notion if that's the case? Or that there's so much variability packed within it that it sort of ends up being meaningless. It's like you have to explain what you mean when you use it anyways. And I do think that that's the case. I think that really we sort of have tended to bin things on the lower, the highest severity end, not wade into the details in the middle. And the mixed severity fire regime idea has been useful in getting us to focus on that. But I think the reality is that there's a lot of diversity there, and that part of what we need to do is work on these tools to be able to parse apart what those differences are, what the unique behaviors are, and those sorts of things.
Great. I'll ask another question. So how do you think climate plays into some of the divergence you've seen in these data sets, like regarding expected fire intervals and severity for different veg types?
Right. I think that's an important question. So we sort of know that in the West, the historical record tends to represent a cooler, moister period, and we can't get beyond that with these data. Really, they just help us define some of these dynamics in that space, and that's of course one of the major potential differences with what we're seeing now, or with near future scenarios, that not only are we seeing things like increases in fire activity, but in a hotter, drier environment. And so that's a hard one. I think that's just a hard one for us, in especially in the tree ring world, to fully address, because we can't quite get back as far as the sort of lake sediment folks, to where we have those major climatic shifts. We're kind of trapped within that. But one of the things that we've been doing, and we have some examples from this project that I didn't share with you today, is trying to pair up some of this data with landscape simulation models and use them to inform what may be happening under these hotter, drier scenarios that we have more limited ability to speak to.
Great. Michael just made a comment and said, no questions, but thanks for the talk.
Yeah.
Okay, we have a question. Jim Allen asks, interesting talk, Dr. Naficy. I don't know a lot about dendrochronology methods, and I'm curious how inferred seasonality works and how reliable it is.
Yeah, this was a really challenging part, especially of our work in Alberta. We were surprised to find in this ecosystem that there were as many apparently winter to spring fires as there were. I mean, the basic method is for, when you look at fire scars, you can see where they fall within or between individual rings. And so if they fall within an individual ring, then you can place that within the early wood or different portions of the early wood versus the late wood. And so that can tell you, if you know something about when the sort of average growing season is and what the phenology is for your region, you can make some inferences about some fairly strong inferences about when those fires generally occurred. And then we have the interring scars, which are those that happen in between two growing years. And if you think about how that works, if one ring grows, then it stops growing, the next one grows. And if you've got a fire scar in between there, that means that it could have happened after this ring stopped growing. So say in the late fall or late summer, all the way through the winter until the spring, up until this ring started growing in the late spring or summer. And oftentimes we calibrate those interpretations based on when we see fires in modern records. So if you're in a system that tends to experience late summer fires the way is common in a lot of the Northern Rockies, or there in the Southern Rockies, before the monsoons, you can make some assumptions that you feel pretty good about. Well, in the case of our ecosystem, we just felt we were seeing some intra-ring scars, much more than we expected, especially for this ecosystem, and then a lot of heterogeneity between samples within small areas. And we made some assumptions, but I don't feel 100% about them. Like, this was a really challenging ecosystem to understand. And we're on some level, we're probably a little bit wrong. I think we did a relatively good job, but we're probably wrong in some cases. But in either case, what it points to is that there was a lot of heterogeneity in the burn season. So we made some assumptions that tended to reduce the heterogeneity between different samples. If we saw in one plot, if we saw intra-ring positions, and then we saw inter-ring positions, and we would assume that those were in the same year. So that reduced a little bit the heterogeneity that we saw, but we still got a lot of it anyways. And so the truth is that this is a really complex question that I don't think we have fully mapped out. It's been based on modern systems and fire regime patterns where there's always some room for error. And again, the missing evidence part here is really just hard. We can't fully know what happened or when a fire happened when the scar is in that dormant position.
Great. Well, thanks again, Dr. Naficy. And if you'd like to, please join us in the discussion. The link is in the chat in about 5-10 minutes. And I think about 10 minutes, I guess they usually take a 10-minute break from what I understand. Sorry, it's my annoying dog. But thanks again. And I really appreciated the talk. And I'm sure everybody else did as well. Thank you.
Thanks for having me. I'll see you guys in a bit.
Thank you.